That's okay. Okay, so -1, so let me just come over here and put this, because this is another formula that everybody should know. When is -1 going to have a Legendre symbol of +1? 1 mod 4, right? And this one will be congruent to 3 mod 4. Ooh, so I know a good question. What's the Legendre symbol of -2 in mod P? Because look, I have that one and I have that one, right? So somehow there's a multiplicative property, so you could like put them together somehow. I won't do it right now, but that's an easy thing to get. Yeah, Jeff?
Well, just going back to 16, so that's a perfect square.
Oh, you just want to do it that way?
Would that be okay?
Of course. I wanted to do this, so I gotta do that. But yeah. Yeah, you can just see right here, -1, this prime is congruent to 1 mod 4, so this is equal to 1. Okay. Take your pick, I don't care. The only thing is, sometimes you don't want to have to feel like, oh, I'm going to have to get lucky to figure these things out. So that's one of the advantages of the quadratic reciprocity law, is it allows you to take these bigger numbers and reduce them to smaller numbers. I mean, you could, for example, take 68 and say, gee, I'm going to add 101 to that. That will give me 169, which happens to be 13 squared, right? But if you didn't see that, you'd be feeling kind of insecure about how you're going to solve these problems. So instead of some trickery here, I just wrote this down like that. It doesn't matter. Okay, everybody all right with that? Okay, super. Okay, so I just told you a second ago that you could probably come up with a Legendre symbol formula for -2 in mod P by putting these two together. But I'm going to do something a little different. I'm going to put together a problem, find it, for the Legendre symbol of -3. Okay? So I'm ready to do another problem. This is number 3. Everybody doing okay so far? Good so far? Okay, good. So here we go. If P greater than 3 is an odd prime, prove that the Legendre symbol of -3 in mod P, this is kind of interesting. So when is -3 a perfect square? For which primes is it a perfect square? It turns out it's a perfect square if P is congruent to 1 mod 6. Okay? So for example, if P is 7, that would be a good example. If P is 7, then -3 is a perfect square. And that makes sense because in mod 7, -3 is the same as +4, and +4 is definitely a perfect square. So the -1 case would be if P is congruent to, well, in order for P to be a prime and to be considered in mod 6, it can't be 2, 3, or 4 because those all have common factors of 6. So the only other option is 5. Okay? Any prime number when reduced mod 6 has to either be congruent to 1 or congruent to 5. It can't be congruent to anything else. Okay. Okay, so this is what we would like to prove. Okay. So how are we going to do that? Well, I'm going to give you a hint here, if I can, to get this started, is that you maybe are thinking you'd like to use a multiplicative property here. And so find the Legendre symbol of -1 and find the Legendre symbol of 3. Of course, the Legendre symbol of -1 we already have well established here, but it's mod 4. It's an equation mod 4. But let's take a look at that. So I'm going to do a couple of cases. So case 1, assume that P is congruent to 1 mod 4. And so in that case, let's look at the Legendre symbol of -3 in mod P. And let's use the multiplication property. So this is -1 in mod p times 3 in mod p, right? It's -1 and 3. Okay. Now, because I'm assuming that p is congruent to 1 mod 4, can I get any help with either of these two parts? What can I say?
1.
The first one is 1, right? Okay, so this is just the Legendre symbol of 3 in mod p. Okay. What can I do with this? Exactly. Flip it over, right? Flip it over again. When I flip this over, do I have... So this is slightly more theoretical because I actually don't know what p is. But I can flip this over. Does it cost me a minus sign or not? The only time it costs me a minus sign is if both of these numbers are congruent to 3 mod 4. But look what we assumed. We assumed that p was congruent to 1 mod 4. So in that case, I can flip this over with no sign change. Okay? So we have that. And now we have to figure out whether p is a quadratic residue in mod 3 or not. Well, what are the quadratic residues in mod 3? I mean, mod 3 is a very small world. So if we take 1 squared, we get 1. If we take 2 squared, we get 1 in mod 3, right? So the only perfect square is 1, basically. So would you guys agree with me that this is equal to, well, it's either 1 or -1. Would you agree with me that it's 1 if p is congruent to 1 mod 3? And it's equal to -1 if p is congruent to 2 mod 3? Those are the only choices. P is either congruent to 1 or it's congruent to 2. Okay, so it looks, so if p is congruent to 1 mod 4 and congruent to 1 mod 3, I'm going to get a +1. If I'm congruent to 1 mod 3 and congruent to 1 mod 4, what can you say about it?
12.
Yeah, right. P would be congruent to 1 in mod 12 in that case, right? So basically, if p is congruent to 1 mod 12, then the Legendre symbol of -3 in mod p is 1. On the other hand, I'm still in this first case though. We're not done. On the other hand, if p is congruent to 1 mod 4 and congruent to 2 mod 3, then we're getting -1. Everybody see that? Okay, so let's put that down. So if p is congruent to 1 mod 4 and congruent to 2 mod 3, and can somebody reduce that for me? If both of these are true, maybe again by inspection, can you tell me what p would be congruent to? There's a unique solution mod 12, right? For p. What would p be congruent to mod 12 in order to make that work? 5, right? 5 works here, 5 works here, and there's only one solution, mod 12, so that must be it, right? So p is congruent to 5 mod 12, then the Legendre symbol of -3 is -1. Yeah?
So if you take that last line really quickly, how the we know that p is congruent to 1 mod 12, p is congruent to 3 and 4.
Mm-hmm.
But how do we conclude that -3 is 1?
Well, because that's what I said right here, is we started with what is the value of this Legendre symbol, it equals this, equals this, equals this, equals this, equals this. We're just going right across the top line. Right?
And since p is congruent to 1 mod 12, it's congruent to 1 mod 6.
That's true, but I'm not ready to get to that yet. I do have that up here as the final thing I'm trying to get to,
Oh, okay.
but let me come back to that in a minute. Right now, I don't want to get ahead of myself. So right now I've said that if p is congruent to 1 mod 12, I get 1. And if p is congruent to 5 mod 12, I get -1. That's all I've said so far. I have a whole other case to do. case 2 is P is congruent to 3 mod 4. And we can go through a similar analysis here. So this would be, this time, the Legendre symbol of -3 in mod P. We would just break it up just like we did before. But this time, what's the Legendre symbol of -1 in mod P this time? -1, right? So -1, and what's the Legendre, oh well, so for the Legendre symbol of 3 in mod P, what would I want to do with that? Flip it? Can I flip it over for free this time? No, this time both of these numbers are congruent to 3 mod 4. So if I want, I can flip it over, but it costs me a minus sign. So I actually get 2 minus signs out of that. And so I have here the Legendre symbol of P in mod 3. So actually, it's coming out the same as it did before, right? This is the same, we ended up with the same Legendre symbol at the end of the day. 2 negative signs canceled out. So I'm just going to get 1 or -1. The first one is, again, if P is congruent to 1 mod 3, and the second one is if P is congruent to 2 mod 3. Now I just need to put these cases together. So if P is congruent to 3 in mod 4 and congruent to 1 in mod 3, what does that tell you modulo 12 about P? Just do it by inspection. 7, right? 7 works here and here. So that's the unique solution mod 12. So if P is congruent to 7 mod 12, then we get a Legendre symbol of +1 again. Okay, so this was my assumption for case 2, and I'm saying if P, so I'm considering P in 2 different mods. That's a little confusing. There's mod 3 and there's mod 4. The mod 4 is what's breaking up case 1 from case 2, but then within each case, I have to have 2 subcases depending on what P is congruent to mod 3. So that's giving me, at the end of the day, 4 different results. The last case is P congruent to 3 mod 4 and P congruent to 2 mod 3. What's the unique solution by inspection? What's the unique solution of that system? 11 is right. Yeah, 11 is congruent to 3 in mod 4 and it's congruent to 2 in mod 3. So P congruent to 11 mod 12. By the way, the numbers that are relatively prime to 12 are exactly 1, 5, 7, and 11, right? Those would be the only numbers you would get for your prime P. Your prime P in mod 12 cannot be congruent to 2 or 3 or 4 or 6 or 8 or 9 or 10, right? Because those all have common factors with 12. So these are the only cases that you can get. So we get a Legendre symbol of -1 in that case. So what you have to do now is just look at, there are 4 cases on the board. Here's the first one. Here's the second one. Here's the third one. And here's the fourth one. And do you see that in these 4 boxes, we have a +1 twice and we have a -1 twice? When do we have +1? Here and here. So you could give an answer and say the Legendre symbol of -3 in mod P is +1 if P is congruent to 1 mod 12 or 7 mod 12. But what's the succinct way of saying that? P congruent to 1 mod 12 or 7 mod 12 is equivalent to what? What you're trying to prove, which is that, right? If P is congruent to 1 mod 12, then it's also congruent to 1 mod 6. And if P is congruent to 7 mod 12, it's also congruent to 1 mod 6. So that's why your final answer is going to be in mod 6, not mod 12. Right? And then what about the other 2 cases? The 2 cases where we have a -1, these 2 here, P is either congruent to 5 or 11. 5 or 11. So put that together. If I'm congruent to 5 or 11 in mod 12, doesn't that just mean that I'm congruent to 5 in mod 6? It's equivalent to that. It's a single answer. So that's it. Yeah, so that actually, we have all of these boxes that are in mod 12, but they are equivalent to, so the 4 mod 12 conditions are equivalent to just 2 mod 6 conditions. I'm going to triple myself if I'm not careful here. Does that make sense? Okay, so that's how it works. That's how it works. So I thought I would show you something really cool that you can do with this. Once you know the formula for the Legendre symbol of -3, we can do another problem. One of the things I really like about the class is that, so you start off pretty early in the semester and you prove that there's infinitely many primes, right? And it's like a fairly standard proof. But then as we've been going along through the semester, we keep revisiting that topic, and we say, oh, well, prove that there's infinitely many primes with the form 4k plus 1. And then I think we did 4k plus 3, right? Using various tools as we were developing them. I'm now going to do another one of those kind of problems using this thing right here. So as a follow-up, and we've done one, there was one of these in the group work as well. So I'm just practicing something that's in the group work for this section of material, which is the following. Show that there exist infinitely many primes of the form 6k plus 1. 6k plus 1. Infinitely many primes of that form. So for every single problem that you've ever seen me do about proving that there's infinitely many primes of a certain form, what was the proof strategy? By way of contradiction. Suppose there's only finitely many. Exactly. So the proof here is by way of contradiction. Suppose we only have finitely many. And let me give them names. I'll just use the same notation that we use in everything else. So P1, P2, ... up to PR. And you don't have to put them in increasing order or anything. You can if you want. It doesn't hurt, but it's not necessary. So here's where, if this was actually on the test, if it was actually on the test, I would give you a hint, because it's a little bit tricky. But suppose that we have all these. Oh, I wanted to say one other thing before I give you the hint. Would everybody agree that each one of these primes has to be at least 7? Well, look what form they have, right? Smallest number you could have of that form would be 7. So note, for all I, piece of I is at least 7. Yeah, okay. We'll probably take advantage of that in a second. Okay, so then here's my hint, is to, you know how we always consider some number? So you guys have seen problems like this before. We usually call it capital M, right? And here's the number that you need to consider, or that you want to consider here. You take the product of all of the primes and you multiply by 2, and then you square that, and then you add 3. Okay. This is the magic number that's going to make this proof work. Okay, so let's see what happens. So, on a couple of, I think I graded one of these on one of the homework assignments at one point, and people were breaking it down into whether n was already a prime or whether it was composite or not, and or some people were doing that. And it actually isn't really necessary to do cases as to whether n is prime or not. You can kind of just do this in one breath, looking at this number. But whatever this number is, it has to have a prime divisor. Even if this number is itself prime, it has to have a prime divisor. Every number is composed of basically the fundamental theorem of arithmetic. Every number has a unique factorization into primes. Okay, so, and is this number even or odd? This is 2 squared is even plus 3, so it's an odd number.
I thought you meant
No, the whole thing.
Okay.
The whole thing. So the whole number n is odd. So if it has a prime divisor, that prime divisor must therefore be odd, right? Okay, so let's just point this out. So note that n is odd, and let's let p be a, I'll put it in parentheses because it's basically implied, odd prime divisor of n. Okay, so saying that p is a divisor of n really just means that in the world of mod p, n is just 0. Does that make sense? Roberto, could you do me a favor and maybe open the door and use that trash can to pop it over? This thing's getting warm in here. I think we keep the door open. Thanks. Hopefully there won't be too much. We're the only ones working today. Okay. Okay, so let's view this as a mod p equation, right? So thus, I'm going to kind of jump ahead here a quick step. Would everybody agree that 2p1, p2, up to pr squared is congruent to -3 mod p? Are we all right on that? Well, if p divides n, right? So I'm saying let p be a divisor of n. So this just means that p divides this whole number.
Oh, okay, I have it.
Yeah. Okay, so modulo p, we have that. So look what happened there. -3. I just erased the first part of the problem. -3 is a perfect square in mod p. So based on this equation, you would have to agree that the Legendre symbol of -3 in this modulus is 1. Because look, -3 is a quadratic residue. Quadratic residue is just a fancy word for perfect square. Right? So you can see that -3 is a perfect square in this mod p. Yeah?
How come we can't suppose that p is congruent to 1 mod 4?
You suppose anything you want.
What if we suppose p is congruent to 3 mod 4 is what I meant? 'Cause
But
then
why
it
would you do that?
Well, because p either has to be of the form, it has to be congruent to 1 or congruent to 3 mod 4, right?
That's true. So we could. So we're taking an odd prime divisor of n. That's all I'm just taking a divisor of n.
Mm-hmm.
And yeah, you're right, it's odd, so it has to either be of the form 4k plus 1 or 4k plus 3. But at the moment, I don't need to use that yet. Maybe we will in a minute, but I'm just going to use this. Because what is this? What did we just prove? What did we just prove in the first part before the follow-up? I erased it. But if if -3 is a quadratic residue in mod p, what's that tell you about p? P is congruent to 1 in mod 6, right? Isn't that what we just proved? That's what we just proved. And if p is congruent to 1 in mod 6, doesn't that mean that it must be one of these guys? Because look, if you are congruent to 1 in mod 6, doesn't it mean you have this form? And we listed all the primes in that form right here. So P is equal to Pi for some I. That's my point. P is equal to Pi for some I. Clear enough? And if P is equal to Pi, well then then what you have right here is basically congruent to 0. All right, maybe I'll say it a different way. So P sub I divides, well, sorry, let me say it this way. P divides 2p1, p2, da 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 da, up to pr squared. Why is that? Because p is equal to one of these primes. So it definitely divides that whole product. So p is going to divide just this part, but p also divides this. So what do? You subtract them. That's what we've done every other time we've done one of these problems. Once you show that your prime divides both of those two numbers, you subtract them and you conclude that p therefore divides what? 3. So since p also divides n, p divides 3, and that is a contradiction. Why is that a contradiction? It's at least 7, right? If you're going to divide 3, you've got to be a very small number, right? The only numbers that divide 3 are 1 and 3. So, so this is contrary to p being at least 7. So that's a nice application. So you first prove what the Legendre symbol of -3 is, and then you use that here to prove that there are infinitely many primes of the form 6k plus 1. And we never did use, Lisa, whether p was congruent to 1 mod 4 or 3 mod.
Yeah,
it just wasn't necessary.
I understand that because
Okay.
because we're already by that equation the thing squared is congruent to -3. We're already saying that -3 is a quadratic residue.
Exactly.
Okay, that's what I
And so you go back now and you try to understand where did this hint come from? This hint was put here because they wanted to make -3 come out as a perfect square. Because they wanted you to get a 1 right here. So how do you make -3 come out to a perfect square? Well, you set capital N equal to this expression, right? And then in the modulus of any divisor of this number, -3 becomes a perfect square. Why did they put the 2 in here? Why not just do this? Then it's going to be an even number, right? And so you wouldn't know, you want to make sure that your p is an odd prime. You can't put if p was 2, we've got a big problem here. We can't do the Legendre symbol on it. So you put this 2 in here to make capital N come out as an odd number. Okay? And that doesn't really hurt the proof though. You just square this whole thing, add 3 to it. Make sense? Okay. So just thought I'd show you that because it's similar to some other examples that we've done. Okay, so I want to get on to a few other things here. Oh, and you guys all know you're supposed to be learning these proofs, right? The five proofs or whatever. Is this thing still going? No, I'm going to just start it over again.